We've walked through the engines and their operation. Let's see it move.
Oh, all right. Well, we start by opening up the throttle valve. And
We are hearing and seeing Monder's engines operated.
yeah, it's a very unusual sound too compared to all other steam engines because of the timing of the engine and the design. It's called 100 degree and 80 degree. It's not 90-90 like some engines. So it's an unusual sound. Part of this concept is that because the piston has a trunk on one side, the surface area of the trunk eliminates some of the power that's produced on that side of the piston. The opposite side of the piston has a full face of steam working against it, but the trunk side is lost, and in this case it loses about 10 to 15% of the surface area, which means that the piston itself is unequal in force produced on the engine, and that adds to the sound you hear that is unusual. While this was unique in configuration, it more than made up for it in performance, and that's because of the nature of the timing on the engine.
And so, as we've discussed and now seeing the valves moving, and now we see the piston moving back and forth, we can actually see it moving the rock shaft, transferring down to the crank, turning the engine. But I think it's interesting, right here, you can see this linkage moving up and down as this is rotating. Can you talk a little bit about what's going on there?
Yeah, the trunk, as it's called, which is a tube fastened to the piston to stabilize the piston so it maintains its perpendicular relationship to the bore of the cylinder. The trunk acts as a stabilizer, but in order to get the motion, Ericsson fastened a piston rod to the head of the piston, and that went back to the rock shaft and transmitted the motion without interfering with the trunk's function of stabilizing the piston.
Because if I have it correctly, right, all steam engines, to make something turn, you have to transfer a straight motion to a rotating motion. And on most traditional steam engines at the time, that was a really long width. So what Ericsson does is he uses this tube as a way to shorten that length. So he puts a pin behind the piston head, which allows the trunk to take the straight motion to accommodate for the rotation. This inner shaft that rides through it can rotate up and down, so as this turns, it allows it to move while the piston is going straight.
Exactly, and the big problem with early steam engine development was converting linear motion into rotary motion, and there were various applications that did it. And this one you're seeing is extremely unique. James Watt supposedly invented the trunk piston, and I say supposedly because he patented it, but he never built an engine with the trunk. But John Ericsson did. Now, the normal trunk engine has the trunk go all the way through, and this is actually called a half trunk engine because the trunk is only half the width of one engine. Instead of going through the entire cylinder, it's only on one side. So the correct term is a half trunk engine, which again makes it a unique application of steam principles.
Okay, so each side is a half-trunked vibrating lever. What does that mean?
All right. First of all, a trunk engine normally has the hollow tube, which is called the trunk, go all the way through the cylinder to both sides. It was a type of engine used on steamboats with paddle wheel steamers. But in this case, John Ericsson only wanted half of that tube, only on this engine on the starboard side. So therefore, it's called a half trunk engine. The vibrating lever term comes from the fact that in 1860, vibrations were not what we know of today. You might call this a vibration today, but that's not a vibration in 1860. Any semicircular motion was called a vibration. So what we see with the arms on the rock shaft is they're inscribing a semicircular motion, so therefore they were called, or it was called, a vibrating lever engine. Ericsson's earlier engine with the Princeton was a vibrating piston engine because he actually had the pistons moving in a semicircular motion. However, in Monitor, the piston is traveling in a linear motion, and therefore he's changing that linear motion into a circular motion, which then transmits the power to the propeller shaft.
And we talk about how unique this engine design is. It makes me often think about the steam engine technology moving on to ships. We think about all the changes that Monitor brought. Can you imagine being an engineer coming out of the ship, or even a crew member, and not only you're seeing all these new things, you're going in an engine room and seeing an engine like you've never seen before.
Yeah, it did require a different mindset. And in the early U.S. Navy images of Ericsson's engine, I'm sure they were pretty concerned about whether that engine would function because it was totally unique compared to the existing engines used on warships and on commercial ships as well.
Thinking about just the uniqueness of the ironclad overall, one of the features that jumps out is the cutoff.
Yeah, pretty important for the overall function of the engine because cutoff saved so much energy cost, and also you have to realize that they'd have to refuel with coal every couple days, and cutoff prolonged that period of time when they didn't have to go to port and refuel. So it was an important concept. Let me run the engine for you, and we're going to show the cutoff in operation. Okay, let me do this. Okay, now this is about the normal speed of the engine, and it would be about 60 RPM. And at that time, the crew member would grab the bypass handle and raise it to put the engine in cutoff. Now it looks extremely rough for you because we're using compressed air instead of steam. We're only giving the engine pistons 40% of the power of air. Air is very inconsistent and doesn't produce the prolonged power stroke that you get with steam. But you can see the result of an interrupted power supply going to the piston, and that was a very energy saving thing because you use less steam, and we're also using less air right now, but air is not the commodity to use to show the operation of the engine. Now we're in normal operation, which would be in battle conditions or emergency situations where the ship needed full speed and power, and they weren't concerned about energy conservation at that time.
And so was the concept of cutoff fairly common at the time period, or is this a new idea or an applied idea that Ericsson brought to the machine.
It was used on other engines, Will, but it also was expensive in building the engine because you needed extra valves and extra controls. And that was a forfeiture. You got energy conservation, but it complicated the engine operation. And a lot of engineers wanted to keep the engine as simple as possible, so they didn't do it.
And is the concept of the cutoff and the use of conservative energy, is this a segue to later on expansion engines?
Yes. This is a set cutoff on here. Later engines actually had variable cutoffs where they could change the timing of the cutoff. And as I said, this is 40% and it shuts off the steam, but the steam expands. With variable cutoff, you can go from 1 to 100%. So they were able to use that as an extra throttling advantage on later ships.
So just like that, the idea of the hairdryer and being able to, if your hair is super wet, having to use full heat on your hair dryer, but then as your hair dried out, you didn't need as much heat, so then you slow your hair dryer down to the lower setting to be able to not use as much energy.
And that would be the same. When they started the ship and would accelerate in the water, then they would engage the cutoff operation so that they would conserve fuel.
Excellent. We've spoken about how unique Monitor's engines are overall and Ericsson's genius, and to really highlight a focal point of that is the reversing gear and what it does for the ship. Can you walk us through how it works, what it controls, and really give us that insight into how revolutionary these engines were?
Yeah, this was an amazing development in engine control technology. At the time Monitor was built, most ships had a reversing mechanism called a slip eccentric, and the slip eccentric would actually require the engine to be stopped, and then the mechanics would get in there, and stopping the engine was not necessarily easy, because if it was a propeller driven ship and you had current turning the propeller, it made it very difficult, where they would actually take the eccentric and loosen it up and rotate it in order to time the engine to run in reverse. The other option for reversing an engine at the time was using Stephenson linkage. Now, Stephenson linkage was very popular, but also is complicated in size. The required size of the Stephenson linkage was a controlling factor on space. And Ericsson realized, looking at the Monitor's engine, and also the Stephenson linkage required double the number of eccentrics. So for a normal running engine without cutoff, you needed 2 eccentrics. But if you were going to use a Stephenson version, you had to have 4 eccentrics. And boy, if you added cutoff, now you're up to 6. So you're really getting complicated with a lot of linkage. And Ericsson came up with his quadrant gear mechanism. And the quadrant gear mechanism is, if I take the eccentrics and rather than having them clamped to the shaft for timing purposes, if I clamp them to a gear, and the gear's position can then control where the eccentrics are relative to the shaft. And he took that bevel gear and he applied 2 quarter gears, which are called quadrant gears. He applied them with a linkage, and he used what is called a throwout bearing. And by moving the quadrant gears in, they actually spin like this. And when they're spinning, they spin the other gear that's fastened to the eccentric. So it was a very unique mechanism, and not used that I can find in my research on any other ships other than monitor type vessels in the Civil War. It's extremely compact, and because it didn't require the extra 2 eccentrics, allowed Ericsson to reverse the engine with only 2 eccentrics for the cutoff and 2 eccentrics for the main valve. Let me just show you what happens. Now, this is the cutoff valve, and we're not concerned about cutoff. We want to reverse the direction of the engine. So I'm going to do it without steam, and as I do this, notice this is the only valve that moves. The eccentric is here, and it's translated over to this valve on the main chest. So notice the movement, and as I reverse the engine, it causes that to move. It doesn't bother with the cutoff. Now I'll go back to forward motion, and notice it's only changing the timing of the main engine valve, and the timing matches the direction that is desired to go on the engine. And right now we're running what is be called a counter rotation, or not counterclockwise, I should say, as you look at it. But this is the direction that the propeller worked to go in forward motion, and that's what we have set here.
So if we think about it, as we go back to our discussion on how a piston moves, on one side of the piston, steam is coming in, pushing the engine in one direction, and the valve inside the chest basically directs the steam flow to push, and then enables the other side to vent out of the engine. And that location within that chest determines which way the pistons are getting pushed. And so by readjusting this arrangement, we're changing the arrangement of the valve, so the intake on one side, which is the outtake on the other, switches, and the outflow becomes the inflow, and we're able to drive the engine in reverse. And those 4 eccentrics sit on the reversing gear shaft, of which the 2 that control the cutoffs, if I understand it correctly, are physically attached. They don't move. They're mounted onto the reversing gear shaft, and they just sit and rotate around as the engine goes. But the beauty of this unique quadrant gear system is the 2 front eccentrics are part of that assembly. And so as it moves, they can adjust as the engine is running.
Yeah, and an important point, Will, is that you could change it from forward to reverse while it was under power. So this is extremely important for basically a battleship. That's a warship, that they could have control to immediately reverse. I mentioned the slip eccentrics earlier, and that would take maybe 2 minutes to reverse the direction of an engine using slip eccentrics. With Ericsson's, the reversing is immediate. I mean, you're talking a few seconds. As fast as you can turn the handle is how quickly you're able to reverse it. Well, let me turn some air on here and run it. Now, it's not as smooth as it will be with steam, but you're going to get the idea. Notice we're turning anti-clockwise here, which would be normal direction for the propeller to propel the ship forward. And if they were running the engine and the captain said go to reverse, they could do it immediately. And they did it by turning the hand wheel, which takes the quadrant gears and actually shifts the eccentrics in operation.
So we're in neutral right now, effectively.
Yeah, we're halfway. And the eccentrics are halfway, which means the pistons don't know which way to run. So we have steam up to the cylinder, but it doesn't know where we want to go. So the seaman would turn the hand wheel about 8 turns and go from a full direction in one way to the other direction. So now we're going clockwise and the engine's in full reverse. And this was really important for warships because it would give you tremendous control of the ship in a very short period of time. And the big thing is you could do it without touching the throttle.
Right.
So it didn't require other movements. It was just turn the wheel and you're going to reverse the engine.
In thinking about that ability to quickly go from forward to reverse, during the Battle of Hampton Roads, it took the Virginia almost an hour to make a complete turn, whereas Monitor could do it in 15 minutes.
Right, right.
And so it just shows you, because the Virginia was a conversion from a steam frigate, and so although it was an ironclad, it still had the innards or the inner workings of a steamship. And so it just shows you the ability. Not only was this engine compact, it also had the capability to function in a new way, enabling advantage during battle.
Yeah. Responsiveness to control, very, very important. You have to get the job done.
Awesome.
Very unique. In my research, only Monitor ships had this reversing mechanism, but his design being so compact made it a revolution as far as reversing engines.